Hi, my name is Peter Karkus, and I will present the Differentiable Mapping Network, a method that learns structured map representations for sparse visual localization. The work was done during an internship with Google Research. Consider the sparse visual mapping and localization task. A robot here needs to map a new environment, given a handful of context images taken from known viewpoints. Then it needs to localize with respect to this map, given a new sequence of query images taken from unknown viewpoints. The task is similar to SLAM, except that here we are given a few pre-collected images from known viewpoints. For example, such image pose pairs could come from the Street View dataset, as shown here, and query images could come from an onboard camera of an autonomous vehicle. What makes this task setting hard is that only sparse information is available to build a map. And even more importantly, the scene may look very different from the time of mapping and the time of localization. So, for example, cars and pedestrians may move, or the seasons or the weather may change, and so on. Similar tasks could arise in a number of other robotics applications as well, like multi-robot mapping or warehouses with frequently changing appearance. To address this task, we need a map representation that is flexible, such that we can learn what features are useful for the downstream localization when some aspects of the scene look very different. At the same time, we want the map representation to be structured, so that it can generalize from limited real-world data. Classic approaches use voxels or point clouds to represent the map. They have strong geometric structure, but they are rigid in what information they can encode, and they are agnostic to the downstream task. We could also cast the problem as a regression task and use deep neural networks. These networks can learn task-oriented latent representations, but they lack structure to generalize from limited data. In this work, we develop a differentiable mapping method that uses a structured map representation, but that also learns what to store in the map in the context of the downstream task. This differentiable mapper is a neural network, but one with specific structure that encodes a geometric mapping algorithm as well as a base filter. The network is trained end-to-end from image inputs to location outputs by providing gradients through all these components. The underlying idea is to treat neural networks as more like general computation graphs, where some nodes correspond to learnable network parameters, but others correspond to fixed operations, like a geometric transformation or an operation of the filtering algorithm. In a similar spirit, a growing body of recent work developed differentiable components of the standard robotics pipeline for mapping, state estimation, planning, and control. This work aims to fill a gap in this space that focus on mapping. To this end, we introduced the Differentiable Mapping Network. The architecture has two components, for mapping and for downstream localization. The mapping component extracts embeddings for each context image using a CNN. These embeddings are stored together with the known viewpoints. So this set of viewpoints and embeddings define our map, which we call the spatial view-embedding map. The map is then used in a differentiable particle filter for localization. The particle filter maintains a set of weighted particles that represent the probability distribution over the unknown location of the robot. In each step, when a new observation arrives, the particle set is updated with a transition model and an observation model, just like in standard Monte Carlo localization. Here, the observation model is learned, and intuitively, it measures if the current observation is compatible with the location on the map. To summarize the spatial information in the map, we use a novel egocentric spatial attention mechanism. The attention mechanism was inspired by how people use maps. We tend to rotate the map and compare it with what we see in front of us. So we do something similar. This is our view-embedding map with 3 view embeddings. Poses are in yellow, orientation in green, and embedding in red. Given a new query observation and a particle for a viewpoint, we first transform the map and rotate it to an egocentric coordinate frame. Then we want to compare features of the query image and the map. To combine multiple embeddings, we use attention over them, where importantly, attention keys are a learned function of the egocentric viewpoint coordinates. The summarized map features and the query image features are then fed to another network that outputs a scalar, estimating the compatibility of the query image, particle pose, and the map. We do this for each particle and use the normalized compatibility values as particle weights. These set of weighted particles then define a distribution over the unknown variables. The exact network architecture we used is described in detail in the paper. Overall, the strength of the approach is that the learned features for mapping and observation model for filtering are all trained together, optimizing for the final localization objective. We ran experiments in 2 synthetic domains from the literature, as well as a real-world domain based on the Street View dataset. In each example, we are given a few context images with known viewpoints, these are shown in green, and 1 or more query image with unknown viewpoints, shown in red. The images are all taken from different 40 by 40 meter large areas. We train with a set of such areas and use the ground truth location as training label. We then test in previously unseen environments. So, for Street View, the test images came from previously unseen parts of Manhattan. Without retraining, we evaluated the models in a number of settings, changing the initial uncertainty, the number of context images, trajectory lengths, and the number of particles. Here, we show the main results on the Street View dataset. We report success rate in percentage, where localization is successful if the root mean squared error is under 9 meters after 5 steps. Our method achieves 73% success on this challenging task. We first compared to alternative map representations from prior work that use a latent image or a latent vector to represent the map without explicit geometric structure. We also tried replacing the particle filter component of our architecture with a simple regression network. All these alternatives perform significantly worse. We also compared to an oracle that predicts the closest known viewpoint at each step. This oracle provides an upper bound on the performance of any approach that's based on similarity of the images. We observed very similar tendencies in the simulated domains. We also evaluated the models in various settings to understand the importance of each of the components. Without going into details, we observed the following. Compared to alternatives, the benefit of our view-embedding map structure increased further when we train in a small data regime. This is probably because geometric structure here acts as a useful inductive bias for learning. The benefit also increased when more viewpoints were given for mapping and when having to map larger areas. This is possibly because our map capacity of the view-embedding map grows with the mapping context, but without making it harder to retrieve the relevant information for localization. Ablations of our egocentric spatial attention mechanism show that egocentric transformations are indeed very useful, while the exact implementation of the attention mechanism provided a little benefit. Comparing localization with the differentiable particle filter and the regressor, we found that the benefit of filtering increases with the trajectory length. This is perhaps unsurprising, as a filter propagates uncertainty through time. Finally, as one would expect, if we increase the number of particles, the performance further improves. This provides an opportunity for us to trade off performance against computation time during evaluation. In conclusion, we introduced a differentiable mapping approach, a component towards the full differentiable robotics pipeline. The differentiable mapping network allows us to learn what to store in the map depending on what is needed in the downstream task. At the same time, our architecture builds in strong geometric knowledge in the form of the view-embedding map representation and the egocentric spatial attention mechanism to read the map. There are promising directions for future work on applications, for example, for an autonomous vehicle to localize anywhere on Earth using Street View data. Our differentiable mapping architecture could also be extended to the full SLAM setting, where new embedding could be added every time a new observation arrives. Thank you for watching.